How's it going, everyone? This is Sal here again with another video for you. Today I wanted to go over Markovnikov's rule in organic chemistry. Markovnikov's rule states that when an unsymmetrical alkene reacts with a hydrogen halide, the hydrogen adds to the carbon that has the greater number of hydrogens. The halide adds to the carbon with fewer hydrogens. And I'll illustrate this with this example of 2-methylpropene. So we have 2-methylpropene here, and first thing I'm going to do is take a closer look at this molecule and see what the hydrogens actually are. So if we take a look at the molecule, we have a double bond right here. Let's see what hydrogens are attached to this double bond. On this side, there's 2 hydrogens. And in case you're wondering how I know that there's 2 hydrogens here, it's a CH2, and a carbon generally has 4 bonds. So the way I like to think about it is this carbon, in order to be satisfied, should have 8 electrons, and thus it should require 4 bonds. So if you look at it right now, if I were to just look at it without drawing these H's, I know that there's a carbon right here, and this carbon has currently 2 and 4 electrons on it, 2 for each bond. Since it's a double bond, it's 4 electrons. And since there's nothing else shown in organic chemistry, we can assume that there are hydrogens attached to complete the octet. And so thus there's 8 electrons on this carbon. So that's how I know that there's 8 electrons on the carbon. But that's just a really drawn out way of explaining that. But in case you were wondering. So anyway, we know that this 2-methylpropene has 2 hydrogens here on this side. Now let's look at the other side of the double bond on this side. On this side of the double bond, let's see how many connections there are. We have a carbon right here. The double bond provides 4 electrons, as I mentioned earlier, and then these 2 bonds provide another 4. So there's 8 electrons here. So this carbon is happy with the octet rule, and there should not be any hydrogen here, because if there were a hydrogen here, this carbon would then have 10 electrons, and that would be violating the octet rule, as carbon likes to have 4 bonds. So that's a quick breakdown of this molecule. So what if we were to react this molecule with hydrogen bromide? What would happen? Let's take a look. So hydrogen bromide has 2, 4, 6 electrons around it, like so. So the very first thing that I would advise you to do when looking at reactions with alkenes and double bonds is to treat the double bond as a nucleophile. And this will help you because reactions typically go from nucleophile to electrophile. So treat this double bond as a nucleophile, and let's see what happens. This double bond will attack this hydrogen right here, and it will kick off this bromine. Okay, so let's see what the product is of this reaction. Once the bromine is kicked off, it will actually form a cation, a carbocation. And this carbocation is a tert-butyl carbocation. I'm going to explain how this is formed. Remember, the bromine is kicked off. Now this bromine, it brings along with it the 2 electrons, which is from right here. Okay, these 2 electrons that were bonded to the hydrogen, it brings it with it over here. Okay, so now let's take a quick look at what happened. I'm going to draw down here. So we have this molecule. We know that there are 2 hydrogens on this side. Okay, the nucleophile, the double bond, attacked HBr and took off this hydrogen from the HBr. Now the question is, where did this hydrogen go? Did the hydrogen go on this carbon, or did it go on this carbon? Now we know from Markovnikov's rule that the hydrogen adds to the carbon with the greater number of hydrogens. And if you look at this carbon, there are 2 hydrogens attached to it. On this carbon, there are no hydrogens. Remember, we spoke earlier and we said that this carbon is happy, it has 8 electrons. There's no hydrogens attached to it. So what does Markovnikov's rule tell us? It tells us that the hydrogen should go on this carbon. And so when we look at that, what should that molecule look like? It should look like this, right? Think about it. This carbon is the same carbon over here. I'm actually going to illustrate it in red. This carbon is the same carbon right there, except it no longer has the double bond. Why doesn't it have the double bond? Well, the bond was broken, and this carbon now has 3 hydrogens attached to it. Well, now we know that this carbon that I've circled here has 3 hydrogens to it, and I'm actually going to draw it out just to make it look a little bit cleaner. So there's 1, 2, 3 hydrogens on this carbon now. So what happened with this carbon? It's actually important to cover that. So let's take a quick look at what happened to that carbon. So okay, so the molecule looks like this. Okay, let's see what happened to this carbon. So this carbon right now has no hydrogens to it, but how many electrons does it have? Take a quick look. 8 electrons, right? 2 from each bond. Okay, now this molecule turned into this molecule, and it turned to that molecule specifically because, as you can see, the 3 hydrogens attached to the other carbon, causing it to basically become a methyl group. Okay, so now this carbon, which used to have 8 electrons, how many electrons does it have now? Let's take a look. 2, 4, 6 electrons. Okay, so this molecule went from 8 electrons, well, this carbon, sorry, went from 8 electrons to 6 electrons. So it's missing, so to say, electrons because it should have 8 electrons. So we should put a positive sign on this carbon because it's a carbocation now. And if you pause the video and rewind and just look at this carefully, it will make more sense to you why this happens. But basically, the carbocation forms once the hydrogen gets attached to the other carbon on this side. Okay, so we know that a carbocation forms. I'm going to put the plus sign right here, as we discussed earlier. We know that a carbocation forms on this molecule. So what's the next step? Well, we have a carbocation and we have a nucleophile, and the nucleophile is the bromine anion that was formed from the original reaction. So naturally, the nucleophile will attack the electrophile. So in this case, this bromine comes and attacks over here, and the final product will look something like this. Okay, so that's the mechanism for this 2-methylpropene when it reacts with HBr. You get this tert-butyl bromide. Let me actually write that. Okay, so you get this tert-butyl bromide. Let's look at a couple of other examples to see what happens. So let's take a look at this example. We have a 2-methyl 2-butene, and we're reacting with HCl. So let's look at it step by step. So we have the molecule. As I mentioned, you should look at the double bond as the nucleophile. So you have HCl over here, and we know that the chlorine is not what's going to be taken out, but it will be actually pushed off from the reaction. So let me go to red here. So this double bond will attack the hydrogen here, taking off the chlorine. So let's see what happens. There are 2 places where the hydrogen can attach, and I'm going to draw that right now. Okay. So the hydrogen has 2 options. It can either go over here or it can go over here. So which side has more hydrogens and which side has fewer hydrogens? Well, let's check it out. Over here we should have 1 hydrogen, because let's look at the carbon, right? 2, 4, 6, 8 to fill the octet. So therefore there has to be a hydrogen here. On this carbon, how many hydrogens are there? Well, let's look at the bonds. 2, 4, 6, 8. It's full. So there can't be any hydrogens on that carbon. So this carbon has no hydrogen, and this carbon has 1 hydrogen. And what does Markovnikov's rule tell us? It tells us that the hydrogen adds to the carbon that has the greater number of hydrogens. So that must mean that it's this carbon. So let's see what happens to the molecule then. The molecule should look something like this now. Now think about it. This carbon that's right here now has 2 hydrogens on it, because remember previously it had 1. Now it has 2 hydrogens, and before in this molecule had 1. So now that this carbon has 2 hydrogens on it, this carbon, how many electrons does it have? Let's look at it. 2, 4, 6. So it's missing 2 electrons. Previously it had 2, 4, 6, 8 electrons, so it was happy. Right now it's not, so we must assign a positive carbocation on that. Now we have, what do we have? Let's take a look. We have this molecule. I could draw that better if I try. Let's see. This molecule, right, with a positive charge right here, and we have this chlorine anion. So obviously the nucleophile will attack the electrophile over here, and you're going to get something that looks like this at the end. Let's do another example. So let's take a look at this molecule. We've got cis-2-butene reacting with HCl. Let's look at the molecule and let's focus on the double bonds. Okay, so we've got one double bond right in the middle of the molecule, and let's look at how many hydrogens are attached. So on this side we have 1 hydrogen, and on this side we have another hydrogen. So this is an interesting example, right? We have the same amount of hydrogens on both sides. So what's going to happen? If we have the reaction, this double bond will attack this hydrogen, kick off the chlorine. At this point, we don't know if the plus sign is on this side or if the plus sign is going to be on this side. And when you look at it, you really can't tell. The hydrogen could attach here, and then you'll have 2 hydrogens here, and the remaining 1 hydrogen will be over here, making this a plus sign. Or we could have the exact opposite, where we'll have 2 hydrogens on this side and 1 hydrogen here, giving this the plus sign. Well, I have an easy solution to this. Since the molecule is symmetrical to begin with, Markovnikov's rule actually doesn't take effect, because if you see up here, Markovnikov's rule is only for unsymmetrical alkenes. So in this situation, either can happen and you'll end up with the exact same molecule. However, what happens? You get a plus sign over here, chlorine is the anion, comes and attacks, you end up with a molecule that looks like this. Or if you happen to do it on the other side, it's going to look like this. It's the exact same molecule. Let's do another example. So let's take a look at this example. 2-methyl, 1-butene. So let's start off again by looking at the double bond. So I have the double bond right here, HCl. The double bond will act as a nucleophile and attack the hydrogen. It will kick off this chlorine. So we form a molecule that looks like this. Question is, where did the hydrogen add? Well, let's take a look at what this molecule had. This molecule, this double bond has 2 hydrogens coming out of it, and this carbon on the end of the double bond has how many hydrogens? Well, let's see, 2 electrons, 4, 6, 8. So it's happy. It shouldn't have any hydrogens on it. So there are more hydrogens on this carbon. So Markovnikov's rule tells us that the hydrogen added to that carbon. So the new hydrogen came in right here. And what happened is this double bond got broken, and we ended up with a product that looked like this. Well, an intermediate. We're not done yet. So now there's 3 hydrogens over here. But what happened to this carbon? Well, this carbon, previously it had 2, 4, 6, 8 electrons. Now this carbon has 2, 4. Now this carbon has 2, 4, 6 electrons. So thus there must be a positive charge on this carbon right here. Finally we have the chlorine anion, which comes in as a nucleophile attacking this carbon, and we get a final product that looks like this. It's probably easier to write it like this visually because it looks neater. If we didn't follow Markovnikov's rule and we said that the hydrogen added over here, okay, then we would have a plus charge on this, which is not stable at all. As you know, it's a primary carbocation, and then the chlorine would attack over here, and we would get a final product that looks like this. But again, this is not formed because this is not following Markovnikov's rule. Let's do another example. Now let's take a look at this example. We have this molecule here on the left, and we're reacting with the HCl. So again, this double bond will attack this hydrogen, kicking off the chlorine. Question is, where does the hydrogen go? Well, if you look at the molecule, this is the double bond, and we have one carbon here to the left and one carbon here to the right. Let's draw out this molecule. So the molecule looks like this, but it can also be drawn in line form. In line form, the molecule would look like this. You would basically have to realize that there is one hydrogen coming out of this double bond right here. Actually, I'll just put it right here so it's easy to visualize. Now, Markovnikov's rule tells us that the hydrogen is going to go to the carbon with the greater number of hydrogens. How many hydrogens does this side of the double bond have? Well, again, we have 2, 4, 6, 8 electrons. So this carbon is happy and doesn't have any hydrogens on it. What about this carbon? Well, we know 2, 4, 6, and now 8 electrons. So this carbon has this extra hydrogen on it, this one hydrogen. So Markovnikov's rule tells us that the hydrogen up here is actually going to come and attach to this carbon right here. So we should get a resulting product looking something like this. Now, where is the positive charge going to be? Again, let's look at this carbon. When looking at this carbon, I'm going to draw the previous structure. So previously, this carbon had how many electrons? This carbon had 2, 4, 6, 8 electrons on it. And we went to a structure up here where this carbon has 2, 4, 6 electrons. So the plus charge should be on this carbon right here. At this point, we're simply doing a nucleophile to electrophile reaction where this chlorine anion will attack the carbocation over here, and we should get a final resulting product that looks something like this. I hope this video helped. If you have any questions or comments, feel free to leave them in the comment section below. And please like, share, and subscribe. Thank you.